it is essentially a continuation of the third lecture. So what was the content of third lecture? There we were addressing the problem of constraint minimization of the suitable distance between y and xb, subject the constraint given by AB is equal to 0. Let me give you the technical details little bit. So the model that we considered in the third lecture, and here also we are going to consider the same model. It is given by y is equal to xb plus e. Alright, and the problem is to find least squares estimate of b subject to AB is equal to 0, where A is a known matrix of full row rank. So that was the problem that we considered in the third lecture, and here also we are going to consider the same problem. So how far did we go in the third lecture? There we noticed that first of all that in the unconstrained minimization, the projection matrix Px onto the column space of X, Cx, which is denoted by Cx, played a very crucial role. So that was the unconstrained minimization. Then after a little bit of technical work, we noticed that the constraint minimization problem can be recognized as an unconstrained minimization problem with some vector subspace V playing the same role as column space of X. So we identified that vector space V. So therefore, now our next goal is to obtain an expression for the projection matrix onto the space V. That's what the technical part in this lecture is, fourth talk is. So in the present lecture, we shall obtain expression for P, V in terms of X and A. And as I told you that our reference for this talks is Seber's 1984 book, Multivariate Observations. We have already stated in the introduction that this is the model y is equal to xp plus e, and we are addressing the question of least square estimation of this B parameter matrix B subject to this set of linear constraints given by AB is equal to 0, where A is a Q cross P matrix of rank Q, full row rank, and there is an additional assumption on capital X matrix that we shall introduce in appropriate time. So let's briefly recall. So in the third lecture, we could recognize that this problem of constraint estimation is actually can be recognized as a unconstrained estimation problem. In the unconstrained estimation problem, the projection matrix onto the column space of X plays a crucial role. In this case, we have identified a suitable vector space V so that the projection matrix onto V will play the exactly same role. And in this lecture, we are going to find expression for PV in terms of X and A. So let's see the model again. Y is equal to xb plus c, X is n cross P, B is P cross D, etc. And these are the rows y1 transpose up to yn transpose, and these are the columns y1 superscript, y superscript 2 up to y superscript d. So what are these rows? Yi transpose, suppose the y1 transpose is the vector of observations on d response variables for the first sampling unit. Similarly for other sampling units going from 2 through n. And these are the columns. This jth column consists of n independent measurements on the jth response. So this is the salient feature of multivariate linear model, namely that in univariate linear model we have observations on only one response variable. Here we have d response variable, and X is the design matrix of size n cross P, B is P cross D, etc. And the assumption, so if we write B is equal to the columns B1 up to BD superscript, E is equal to E1 epsilon 1 transpose epsilon n transpose, etc. So we see this relationship that we have already discussed in our third lecture and also even before that. And the assumption about these rows, these are the assumption is that each row recognize, if you turn it into a column vector, it will have expectation 0, dispersion sigma, and their across rows they are uncorrelated. So exactly same setup, the setup that we are working with. Let's remind ourselves again that in this problem, when we are talking about minimizing some quantity, so that's a way we are minimizing a matrix. So therefore, we have to have some notion of comparing to matrix. We introduce for two symmetric matrices C and D C greater than or equal to D if C minus D is non-negative definite. So that's the criteria for comparing two symmetric matrices, and here we recognize this quantity as a function, as a 1 in function of B. So we minimize this subject to AB is equal to 0, where A is a known matrix of rank Q. So this is the problem we are addressing. Y minus X beta transpose Y minus X beta as a function of B, where Y is of size n cross D, X is size n cross P, B is size P cross D, etc. Subject to AB is equal to 0. We in addition assume that X is of rank P, that's X is of full column rank. This will imply that this X transpose X is a P cross P non-singular matrix. It will have a crucial significance in our calculation. What we also did, we have seen that in the unconstrained estimation problem, projection matrix onto the column space of X played a crucial role. In this case, we have tried to take in the same approach and succeeded. What we did, first of all, we define this matrix capital A post multiplied by X transpose X inverse. And notice that AB is equal to 0 if and only if A1 theta is equal to 0. What is theta? Theta is X beta. So we are transforming the argument involving B to arguments involving theta. Why? Because X is a full column rank, so XB, and if we XB and XP, they are related in a 1-1 manner. So, and therefore once we write theta for this X beta, then what do we see? We see that the columns of theta, they are elements of column space of X, number 1. Number 2, the condition AB is equal to 0 can be written in the form A1 theta is equal to 0. So therefore this problem, the problem that we are addressing here, this problem has this alternative version, namely that minimize Y minus theta transpose Y minus theta as a function of theta subject to the columns of theta lying in V. What is V? V is column space of X intersection null space of A1. Why? Because first of all, once we write this theta, columns of theta are elements of column space of X, number 1. Number 2, theta satisfies this. That means each column of theta, it's an element of null space of A1. So that's what the problem is. So as we state, our goal is now to find an expression for PV, and that's the crux of this fourth lecture. So since V is a vector subspace, we see that we have achieved a fair considerable technical simplification. We have seen earlier that in the unconstrained minimization, Cx played a very crucial role. Now the same role is expected that the same role will be played by V. But the problem is technically much more harder. Why? Because for Cx we have a neat expression for the projection onto this space, but now we have to handle this space V. So even before finding out an expression for the quantity we are looking for, we see that the unique least square estimate of theta subject to AB is equal to 0 or equivalently A1 theta is equal to 0 is given by PVY. Let us recall what is exactly the same as the early calculation where we had PXY here, right? So in that case, we didn't have this additional part, namely null space of A1, we only had PXY. So PV represents orthoprojection onto V, and this last quantity we denote by theta hat H. Why H? Because H is some abbreviation for maybe a hypothesis. Since X is a full column rank, we have the unique representation theta hat H is equal to X BH hat, where BH hat is the required restricted least squares estimate of B. I repeat that this is the problem that we are addressing, and what we have done is that we have replaced the problem of finding the estimate of B into problem of finding estimate of theta subject to A1 theta is equal to 0, and theta is also the columns of theta are in column space of X. So what we do now, we have to therefore find an expression for this theta hat H. We notice that basically we are projecting the Y vector, each column of Y, to the vector space V. So we need now V is this column space of X intersection null space of A1, So therefore let us, this is an identity, PV is equal to PX plus PV minus PX. Notice that this Cx, V is a subspace of Cx, alright, Cx intersection this. So what we shall do, let's see. So this is Px plus Pv minus is an identity, and if we write down Px minus Pv, then So what is Px minus Pv? It is really within Cx. It is within Cx the ortho complement of V. I repeat, V is a subspace of Cx. So therefore the ortho complement of V within Cx, that is Cx intersection V parp, where V parp is the orthogonal complement of V, and the projection onto this space is given by Px minus Pv. So this Pv is equal to therefore Px minus this. So therefore, as we noted short while ago, that theta h hat is x bh hat, where is equal to Pvy. We have also argued before. So this is Pxy minus this projection applied to the y matrix, and this Pxy is xb hat. So that is the earlier estimate, unconstrained least square estimate b of b pre-multiplied by x minus this object. All right. So what we do now? So we have therefore come to a little bit of simplification. We have seen that theta hat h is, if you call it theta hat, minus p cx v parp of y. So this is the object we have to explore now. So that's our goal now. So p cx intersection v parp of y. So now let's see. So cx is this intersection. What is v is this? Cx intersection na1. A1 is A x transpose x inverse. It is this. It is this, right? So how do we go about it? There is a result in Saber's book. It's a standard fact in linear algebra, where we learn projection matrices, projection onto subspace of a space, etc., and then appropriate argument involving orthogonal complement, etc. That shows us that if we look at this expression, basically you get this column space of Px A1 transpose. So this result, this first one is an identity. Identity means basically we are replacing here in place of V, Cx intersection null space of A1, ortho complement of that. And this is equal to the fact that this intersection is equal to column space of Px A1 transpose. It's a standard fact in linear algebra which we shall make use of here, and a proof of this fact appears in Saber's book, page 535, which we are not producing. So let us recall now, what is A? A1. A1 we have defined it to be A x transpose x inverse. Let us remind ourselves that we have already assumed that capital X is a matrix of size n cross p with full column rank. So therefore x transpose x is Px. So therefore this is Px A1 transpose turns out to be A1 transpose, and so therefore P of x, this is A1 transpose. So we have to see this part carefully. This A1 transpose should be x transpose x inverse, because it's a symmetric matrix. So inverse of symmetric matrix transpose is this same quantity, but this x is the bothering part. We have to check it. We'll see the calculation again. This implies in turn Px A1 transpose, assuming this to be correct, Px this pre-multiplied by Px times x is this, so x inverse a term, that is A1 transpose. So therefore P Cx V transpose, let us look at this, which is same as C Px A transpose, so Px A1 transpose. So therefore C of A1 transpose is now, what is the formula for P of x? It is x transpose x inverse x transpose. So therefore we have this A1 transpose. First of all, A1 is this, so x transpose x inverse, etc. So this is the expression. So what do we get now? We see that x, from what was the preceding step? Our preceding step was this, theta hat h is xb hat minus this. So xb hat h is xb hat minus this. So we have obtained now an expression for this. What is the expression? Xb hat minus x. One should do little bit of calculation in taking a piece of paper and pen. This x, this inverse A transpose, etc. inverse A x transpose x inverse x transpose y. You need not put a bracket there. So I pre-multiply by x transpose throughout. Then x transpose x b hat h, x transpose x b hat x, this cancel each other. I get this. Alright, so what do we get now? We get the following, that if we pre-multiply by x transpose x inverse, I get b hat h, b hat minus, etc. right? And pre-multiply by this means here I am pre-multiplying by X transpose X inverse. Now if we just mechanically multiply this both side by A, we shall see that A BH hat is equal to A B hat A X transpose X inverse A transpose. So this part cancel each other. So A B hat minus A B is equal to 0. And if we see carefully this constrained least square estimate, it is the unconstrained minus the adjustment term. And if one goes through little bit carefully, one will see that why this should be the adjustment term. So therefore, what was our goal? Our goal was that we should be able to obtain an expression for the constrained least square estimate of B in terms of X and A. What were the technical assumptions that we have needed? Namely, two assumptions. One is capital A is a matrix of full row rank, capital X is a matrix of full column rank. Under these two assumptions, we have been able to obtain neat expression. It is possible to obtain expression for this estimate even otherwise if we relax the assumption of capital X being of full column rank, but little assumption about capital is always required. We cannot put an arbitrary restriction. So it is this. So that's what we have done in this third and fourth lecture. And one inquisitive reader, I would request him to look at Saber's book, one see the calculation and see how it goes when this assumption about X is relaxed to non-full rank situation and capital is replaced, not assumed to be of full row rank but something else. So that's where this fourth lecture concludes. So we have in the first four lecture looked at unconstrained minimum estimation of the parameter matrix B, then maximum likelihood estimate, estimation of sigma, some properties, some distribution theoretic property of the estimates, and in the third and fourth lecture we have worked out in detail the expression for the constrained least square estimate of B, and one crucial technical result that is used here and proved in Saber's book, page 535. Let me state again what we have done in the third and fourth lecture and explicitly emphasizing the part in fourth lecture. So we have considered the multivariate linear model y is equal to xb plus c with standard assumptions about x, etc. The problem in this third and fourth lecture that we have considered is find least squares estimate of B subject to AB is equal to 0. So that's a linear constraint, set of linear constraints on the parameter matrix B, where A is a known Q cross P matrix of rank Q. So if we look at the third and fourth lecture combined together, we shall see that there are certain steps. First, we have noticed that in the unconstrained estimation problem, the projection matrix Px onto the column space of X, which is denoted by Cx, played a very crucial role. Then in the constrained estimation problem, we identified a vector space V so that the projection onto V plays the same role as Px did in the unconstrained estimation problem. There we concluded the third lecture. So in this fourth lecture, we have primarily spent time to find an expression for PV, that is new space that we have obtained, expression for PV in terms of X and A. So that's where we concluded, and so we have seen a neat expression for closed form expression for the estimate of B. In the additional assumptions that we have made is there are two crucial assumptions. One is capital A matrix, the matrix giving the linear constraints, the rows are linearly independent, and the capital X, the design matrix, it is the columns are linearly independent.